Dr. Kara Mahler. I work as a senior software engineer at Qcontrol here in Berlin, and today I'm going to tell you about some of the technology we're developing at Qcontrol and how we apply it to customer use cases. So, as we all know, the reason that most of us are here today is quantum computing will have broad applicability across all industries. But why are these opportunities not currently being taken advantage of? The reason is hardware errors. So hardware errors are blocking the practical use of quantum optimization at an industry scale. This issue of hardware errors, which we know is holding back the adoption of quantum technologies in industry, is the exact thing that we try and address at Qcontrol. So at Qcontrol, we build AI-powered error-reducing infrastructure software to make today's quantum computers useful. And we do this by addressing the different layers of the quantum computing stack, focused on the physical qubit layer, down where the qubits live, all the way up to the algorithm layer. So we have different products for quantum computing, which are focused on all the different layers of this quantum computing stack. So the first one I'd like to point out is Black Opal, which is an educational tool which allows users with zero background in quantum to understand how quantum computers work up until the point where they're able to program them themselves. We also offer a tool called Boulder Opal, which is a tool focused for hardware researchers, so the people working on the physical qubit layer of the hardware stack, to help automate and optimize for quantum hardware. And finally, our final product, which will be the focus of today's talk, is Fire Opal. So this is for the algorithm developers and the end users. And this tool is designed to help achieve, for users to help achieve maximum performance from their quantum computers, or from the cloud quantum computers. So how does Qcontrol work? So we offer a complete, Fire Opal offers a complete autonomous tool chain to suppress errors everywhere they occur. So each of the purple boxes shown here is a part of the quantum computing stack where an error can occur and where we have developed technology to address those errors. So each of these purple boxes was developed by intense research from our team, our large team of physics PhDs, researchers, and engineers. And we package this state-of-the-art technology into this error suppression pipeline that we give to users to use with a single line of code, so fireopal.execute, which allows you to execute your circuit and extract the maximum value from the quantum computer. So we do this through methods of depth reduction, error-aware hardware mapping, crosstalk elimination, and gate optimization. And we also have some measurement error mitigation post-processing techniques for after the quantum device. So using Fire Opal, we can unlock latent performance on any application at full device scale. So what this means is that we can run 10 times deeper circuits, which allows you to solve bigger problems. We can reduce shot count by more than 1,000 times, which allows you to do more for cheaper and for less time. And overall, we see a performance enhancement of over 1,000. Some references you can find here, including our benchmarking website, which allows you to find out how you can run some of these benchmarks using our tools for yourself. So we also have within FireOpal, a optimization solver. This is a hybrid algorithm that's used for optimization use cases like the one seen in the previous talk, which combines with quantum and classical resources. So the idea is that you can put in your objective function, which defines the optimization problem you want to solve, and without having any knowledge of quantum circuits or how quantum algorithms work, we solve the problem, or the solver solves the problem for you using a combination of our error suppression technique and our optimization engines, and returns with high probability the correct solution. So to give you an example, this is an example of a max cut problem that was solved using our Q-control optimization solver. So max cut, you have a graph like what you see here, and you want to cut the graph and to maximize the edges. And you can see here that this problem becomes hard as you increase the number of nodes and you increase the amount of connectivity. And using a brute force solver, you see that we aren't able to find the correct answer. But using our Q-control solver, we get the correct answer with very high probability, which is shown in the purple. And what this means at 156 qubits is that we are no longer, the errors are no longer the roadblock, but in fact, the size of the device is the roadblock. So at this stage, we have not achieved quantum advantage yet, because our state-of-the-art classical solvers can solve this problem still faster. But you can imagine once the device sizes are bigger, we'll be able to solve problems that our classical solvers can no longer solve. So now I'd like to talk about some use cases that we have delivered to our customers as the solutions team. So I'm part of the solutions team here in Berlin. And what we do is we co-design quantum solutions across different industries. So just to name 4 of the many use cases that we do. So we have a project with Network Rail in the UK for train timetable scheduling. We also just finished a project with Mazda on vehicle component design. We also had a project with Transport for New South Wales in Australia on real-time transport routing and EV charger placement. And finally, we did some work with Airbus and BMW Group on supply chain logistics optimization. So when I say co-design, what does that mean? Oops. So co-design means a customer comes with us with a use case. We look into how to map their problem onto a quantum algorithm. What might be the best quantum algorithm? Is it even feasible on today's quantum hardware? Are there tricks that we can do to make it run efficiently on today's quantum hardware? And then together with the customer, we co-design the problem, understanding all of the constraints and the complexities of the use case. And sometimes this involves designing a custom interface so that the problem can be solved with our FireOpal and other Q-control tools. Then we normally do a lot of benchmarking, which always involves understanding the state-of-the-art of how to solve the problem classically. So what are the attributes that make a problem viable or interesting for us when we're thinking about achieving commercial quantum advantage? So one is complexity. Complexity in both of the sense of mathematically complex, but also practically complex. So if a problem can be solved easily, classically, then there's no reason for us to try to use quantum for it. We also consider the impact. So we want to be able to prove that even a small improvement over the state of the art gives a lot of value to the customer. And then finally, the resource efficiency is very important. So we want to make sure that the industrial problem sizes, so the sizes of we're no longer caring about toy problems, but looking at the problems that on the real scale that they exist, will fit on our near-term quantum hardware. So that means that we spend a lot of time mapping the problem in a hardware-efficient way. So those were the criteria for what makes a quantum problem interesting for us. So now I'll go into some details about two of those problems that we found interesting and went to solve together with the customer. So the first one is a partnership with Mazda on vehicle component design for fuel efficiency. So designing safe and fuel-efficient vehicle frames is a very simulation-heavy and expensive task. It involves extensive structural simulations, which is required to balance safety and fuel efficiency. So you could think like machine learning models can be used here to identify patterns from previously simulated designs, and these models can be used as surrogates to approximate new designs. So this is exactly what we looked at with Mazda, was whether we could use actually quantum machine learning models as surrogates in their design process. So what this means is we have some sort of optimization loop. Our optimization engine gives us a frame design, so the coordinates that define a car body frame, and we use our surrogate model, which is trained on past simulation data, to tell us the strength of the frame design. And when we use that inside of a loop to find an optimized frame design. So our initial tests have shown that quantum models show very promising improvements in the low data regimes. So this is when you have not a lot of simulation data to train your machine learning or quantum machine learning model on. This might be useful in that scenario, which is the likely scenario when you have a expensive design process such as this one. So here we show what embedding a quantum machine learning model into a real design, engineering design workflow can look like. So in this case, we have a quantum support vector machine, which is trained on just 250 simulation data points, and on a simulator. And at each stage, you see the frame shape is being coming from the optimizer, and the support vector machine is predicting or approximating this objective value. So the next topic I want to touch on is on the network rail problem that we solved with Network Rail in the UK. So this is a station routing problem. So the problem is they want to assign optimal platforms and routes to all trains passing through a station. And here we want to maximize the station capacity, favor preferred routes, and avoid any conflicts. As you can imagine, this is a large solution space with very complex constraints due to safety and signaling requirements. But it turns out that this can be modeled as a maximum weight independent set, which can be solved efficiently using our Q-Control fireable optimizer. So here you actually see the results of what was achieved over the course of this project. So using 26 trains, so this used real data from the London Bridge Station in London, which involved 26 trains, 15 platforms, and in an 18-minute repeating time period. And using some pre-processing techniques, which we implemented over the course of this project, we were able to efficiently map this problem, which started with requiring 448 qubits down to 103 qubits, allowing us, of course, to tackle a much larger problem than initially we thought we could tackle. And you can see here from the top graph that we are able to, with high probability, get the optimal solution. And we benchmark this against a local search technique, which is not able to reliably find the optimal solution. So as a final step in this project, we looked at where we think, or when we think we will find optimization, quantum advantage for this sort of station routing optimization problem. And so you can consider using our efficient efficient problem mapping that we found that I showed you on the previous slide. You can map the problem to to understand how it scales, and then match that up with the roadmaps from the quantum hardware companies such as IBM. And you can see what we implemented compared to what we think we can implement in the coming years. So solving the whole London Bridge problem, so we only solved like a part of it. So solving the whole London Bridge problem, you can see, would fall into this purple box, which is where we consider it to be quantum advantage. This is when the size of the problem gets very hard, or too hard to solve on using the classical techniques. So here we are seeing in between 2027 and 2028, we think that we will see quantum advantage for such use cases. So that's all I wanted to say today. If you have any questions about the products that we offer, since I mentioned 3, or the other use cases that we have worked on, we have a booth right outside this door, so please stop by and feel free to discuss with me and my colleagues that are here. So thank you.